Welcome to a lesson on the diagonalization of matrices. Let's first define a diagonal matrix. A diagonal matrix is a square matrix with all zero entries above and below the main diagonal. If matrix A is a diagonal matrix, then matrix A raised to the power of P is equal to the diagonal matrix where the entries along the main diagonal are the entries of matrix A raised to the power of P. Let's look at some examples. The square of the matrix 2, 0, 0, 3 is equal to the matrix 2 squared 0, 0, 3 squared. The cube of the matrix 2, 0, 0, 3 is equal to the matrix 2 cubed 0, 0, 3 cubed. And the fourth power of the matrix 2, 0, 0, 3 is equal to the matrix 2 to the fourth 0, 0, 3 to the fourth. You may want to pause the video and verify these products. But what we should notice is that if we have a diagonal matrix, it's fairly simple to determine the matrix raised to the power of P. And this is why it can be helpful to diagonalize a matrix that is not a diagonal matrix, which we'll see shortly. An n by n matrix A is diagonalizable when there exists an invertible matrix P and diagonal matrix D such that matrix A is equal to matrix P times matrix D times the inverse of matrix P. This product is the diagonalization of matrix A, and the reason we care about this is once we have it in this form, we can easily determine matrix A raised to a power where matrix A raised to the power of K is equal to matrix P times matrix D to the power of K times the inverse of matrix P. We'll take a look at this formula in just a moment, but let's first verify the diagonalization of matrix A below. So we're given matrix A, and we're told it's diagonalizable, and we're given matrix P, matrix D, and the inverse of matrix P. To verify the diagonalization, we need to verify the product of matrix P, matrix D, and the inverse of matrix P. So multiplying from left to right, the product of the first two matrices is the matrix 1, 8, negative 1, negative 12. Then we multiply by the matrix 3, 2, 1, 1, which does give us matrix A, the matrix 11, 10, negative 15, negative 14. And again, you may want to pause the video and verify the products. Now, not all matrices are diagonalizable. If we take a look at the diagonalization theorem below, an n by n matrix A is diagonalizable if and only if A has n linearly independent eigenvectors. So the diagonalization process of a matrix is an eigenvalue eigenvector problem. And we can also say that an n by n matrix A with n distinct eigenvalues is diagonalizable. It's also true that the diagonalization of a matrix is not unique. And now let's look at the formula matrix A to the power of K equals matrix P times matrix D to the power of K times the inverse of matrix P. Let's do this by considering matrix A to the fifth power. If matrix A is diagonalizable, we know matrix A is equal to matrix P times matrix D times the inverse of matrix P, and therefore we'd have 5 factors of the product. And now if we regroup the products here, notice how we have 1, 2, 3, 4 products of the inverse of matrix P times matrix P, which would be equal to the identity matrix. And therefore simplifying, we have matrix A to the fifth power is equal to matrix P times the fifth power of matrix D times the inverse of matrix P. So while this doesn't prove the formula, hopefully you can now see where it comes from. So let's go back to the previous problem and now find matrix A raised to the fourth power. We already have the diagonalization of matrix A, and therefore the fourth power of matrix A is equal to matrix P times the fourth power of matrix D times the inverse of matrix P, which is set up here on the right. For the first step, we'll determine the fourth power of the diagonal matrix 1, 0, 0, negative 4. Well, 1 to the fourth is equal to 1. The fourth power of negative 4 is equal to 256. And now we multiply the 3 matrices from left to right. Multiplying the first 2 matrices, we get the matrix 1, negative 512, negative 1, 768. And then we multiply by the matrix 3, 2, 1, 1, which gives us the final result. A to the fourth power is equal to the matrix negative 509, negative 510, 765, 766. And again, you may want to pause the video and verify this result. And now let's talk about the steps to diagonalize an n by n square matrix. Step 1, let D be the diagonal matrix with the eigenvalues lambda sub 1 through lambda sub n entries along the main diagonal. Step 2, we find n linearly independent eigenvectors, which we'll call the vectors p1 through pn. And then we let matrix P be the n by n matrix with columns formed using the eigenvectors. So again, we find the eigenvalues to form the diagonal matrix D, and then we find the corresponding eigenvectors to form matrix P. So we do have to have the eigenvectors corresponding to the eigenvalues in the same columns as matrix D, and then we have to find the inverse of matrix P. And again, a matrix is only diagonalizable if and only if it has n linearly independent eigenvectors, or if an n by n matrix has n distinct eigenvalues. Let's walk through an example. Let's diagonalize the given 2 by 2 matrix. We begin by determining the eigenvalues. To do this, we need to solve the equation, the determinant of the difference of matrix A and the product of lambda and the identity matrix equals 0, which I've shown below. The determinant is equal to the product of negative 7 minus lambda and 3 minus lambda minus the product of negative 2 and 12. Simplifying, we have a factorable characteristic equation. We have lambda sub 1 equals negative 3 and lambda sub 2 equals negative 1. Because we have two distinct eigenvalues, this does verify the matrix is diagonalizable. And we also now know matrix D, the diagonal matrix, has negative 3 and 1 along the main diagonal. The next step is to find the two corresponding eigenvectors to form matrix P. So for lambda sub 1 equals negative 3, to find an eigenvector, we need to solve the equation, the difference of matrix A and lambda times the identity matrix times vector x, where vector x is an eigenvector, equals a 0 vector, which I've set up below. Notice how I subbed in negative 3 for lambda. Next, we can write the matrix equation. Let's verify this coefficient matrix. The first entry is negative 7 plus 3 times 1, which is negative 4. And then we have negative 2 plus 3 times 0. In row 2, we have 12 plus 3 times 0, and then 3 plus 3 times 1, which gives us 6. And then we have the augmented matrix, and also written in reduced row echelon form. The first row indicates x1 plus 1 half x2 equals 0. x2 is a free variable, so we have x2 equals x2. To parameterize the solution, let's let x2 equal t, and therefore x1 is equal to negative 1 half t. All the eigenvectors corresponding to lambda sub 1 equals negative 3 are in the form of t times the vector negative 1 half 1, or all the scalar multiples of the vector negative 1 half 1, excluding the 0 vector. So we can use any eigenvector corresponding to lambda sub 1 equals negative 3. For example, if we don't want to use fractions, we could let t equal 2. If t equals 2, we have the eigenvector negative 1, 2. We will use this for the first column of matrix P. So again, notice how lambda equals negative 3 is in the first column of matrix D, and therefore the corresponding eigenvector must be in the first column of matrix P. And now we need to find an eigenvector that corresponds to lambda sub 2 equals negative 1. Going through the same process, to parameterize the solution, we can let x2 be t again, and therefore all the eigenvectors corresponding to lambda sub 2 equals negative 1 are in the form of t times the vector negative 1/3 1, or all the scalar multiples of the vector negative 1/3 1 except the 0 vector. And again, if we don't want to use fractions, we can let t equal 3. If t is equal to 3, the corresponding eigenvector would be the vector negative 1, 3, which is the second column for matrix P. Also notice how the vectors negative 1, 2 and negative 1, 3 are two linearly independent eigenvectors. So the last step is to find the inverse of matrix P, which I've shown here in the middle. So now that we have the inverse of matrix P, we do have the diagonalization of the given matrix. So if we call the given matrix matrix A, we know matrix A is equal to P times D times P inverse, which we see here in blue. This is what we're trying to find. To verify this, we can find the product, and notice how if we do multiply the three matrices, we do get matrix A. We will look at more examples in more detail in the next several videos. I hope you found this helpful.